In this video, I'll go very briefly over hybridization, molecular geometry, and shape. So let's start with hybridization. What is hybridization? Hybridization simply shows the orbitals the central atom need to connect with the groups around it. You already know that we have four subshells. We have the S, we have the P, we have the D, and we have the F, right? So the S subshell is made up of one orbital, and every orbital has a capacity of 2 electrons. The P subshell is made up of 3 orbitals. The D is made up of 5, and the F is made up of 7, which with a total capacity of 14 electrons. Okay, so when we talk about orbitals, we talk about these orbitals in there. So the S is simply one orbital. The P is 3 orbitals in there. These are 3 orbitals. The D is 5 orbitals, and the F is 7 orbitals. So when we want to determine the hybridization, this is solely for the central atom, you guys. What we do is we count the groups around the central atom, and if there's a lone pair in there, we consider the lone pairs as a group. So we would say that every group is an orbital, and every lone pair is an orbital as well. So let's say, for example, if I have this molecule over here. So what is this? This is actually a central atom that is connected. See, let's count them. 1, 2, 3, and 4 groups. So you have 4 groups in there, and there is a lone pair. So what you have here on the central atom, this is a lone pair. It's a one lone pair, which is made up of 2 electrons. So if I want to go ahead and check the hybridization of the central atom now, I'm going to go ahead and count how many groups are there around this central atom. You have 1, 2, 3, and 4. So here what you have is 4 groups around the central atom. And then the number of lone pairs that you have over here is 1. As we mentioned earlier, hybridization is solely for the central atom because it explains how many orbitals the central atom is using to connect to the groups around it. And the lone pair is considered to be group. Okay? So now if I want to calculate the total number of groups around the central atom, this is going to be 4 plus 1. So I'm going to end up having 5 groups. We're going to relate the number of the groups to the number of orbitals, and we will say, okay, I have 5 groups now around the central atom, so I need 5 orbitals now in order to connect to those 4 groups. So what are these 5 orbitals? I know that the S is 1 orbital. The P is 3 orbitals in there. So this is a total of 4 orbitals. Then I would need just 1 orbital from the D. And then my hybridization in this case is going to be, so I need the S, I need the 3P, and I need the D. So my hybridization now is going to be an S and the 3P's. I need all the 3P orbitals, and I need just 1D orbital. So this is going to be my hybridization. This is how much orbitals I need so that this central atom will connect with those 5 groups around it. Let's have another example. This is a molecule there, and this molecule is made up of a central atom, and then it's connected to see how many groups in there. It's 1, 2, 3, 4, and 5. It's connected to 5 bonds, so it's going to be 5 groups. And how many lone pairs? It's 1 lone pair in there. So I need a total of 6 orbitals. It's going to be 6 groups, right? So I'm going to need 6 orbitals here. So what are the 6 orbitals? I know that I have my S orbital. This is 1. I'm going to take all the 3P orbitals. And this is going to be 4 now. I still need 2 more, so I need 2 from the D. So now my hybridization is going to be an sp3, and it's going to be a D2. Okay? Let's have more example in there. More examples. So it's going to be my central atom, and these are the 2 groups around the central atom. So I have 2 groups, and see how many lone pairs now I have? This is going to be 1, and that is going to be 2. So I have 2 lone pairs. So that is a total of 4 groups. So 4 groups requires 4 orbitals. It's the same number of groups is related to the number of orbitals in there. So I need 4 orbitals in there. So if I need 4 orbitals, I know that I would need the s, and simply I need all the 3 p's. So now my hybridization is going to be an sp3. Okay, let's see if I have more examples over here and I ask you, okay, I give you those 4 structures. I want you to find the hybridization. Now, finding the hybridization, I mean by that the hybridization of the central atom. So you are going to highlight that central atom and we're going to see what is the hybridization of the central atom. Again, this means how many orbitals I need so that I can do the connection with the groups around the central atom. So for the first structure over here, this A is connected to, this is one group, this is another group, and I have a lone pair. So actually I have 3 groups over here. So I need the 3 orbitals. So if I need the 3 orbitals, then the hybridization for A, it's going to be an S, and I only need 2 p's. That's it. So these are my 3 orbitals in there. So the hybridization of A is going to be an sp2. Same thing for this one, this A over here. See how many groups are there around it? It's the 3 groups around it. There is no lone pairs, just the 3 groups. So I need the 3 orbitals, then the hybridization is going to be an sp2. Same thing for A over here for the central atom. Again, this is a group. This is another group. This is a third group in there. I don't care about the double bond. It's still a group that is connected to the central atom. So count the groups and relate this to the number of orbitals that you need. So I have 3 groups in there. So since I have 3 groups, I need 3 orbitals. So again, the hybridization is an sp2 hybridization. For the last one, this is going to be my central atom. So I need to find the hybridization. Check the groups around it. There are 2 groups around it. So 2 groups. I only need 2 orbitals. So the orbitals needed here are just the s and the p. Just 1 p. I don't need more than that. So now the hybridization of A is going to be an sp. That's for the hybridization. Now for the molecular geometry and shape. What's the difference between them? Simply, whenever you have a central atom, you want to see how, what is the orientation of these groups around that central atom, including the lone pairs. So when I'm talking about the geometry, I'm talking about the arrangement of the groups around the central atom. Now, when do I start taking the lone pair into consideration? Whenever I want to get the shape of the molecule, because there's a difference between the geometry and the shape. Now, the shape is still the arrangement of the groups around the central atom, but whenever there is a lone pair. So the geometry is always similar to the shape unless you have a lone pair. So once I have a lone pair on the central atom, the shape is going to be different. Why? Because the lone pairs are going to squish the bonds. So the bond angle is going to be less than what is expected. We shared with you the VASPER table. And this VASPER table include those columns, the static number, the number of lone pairs, the geometry, and the shape. You can easily see that the geometry is similar to the shape when there is 0 lone pairs. But the moment you have a lone pair, the geometry is going to part from the shape. The shape is going to be different, of course, with the exception of the first static number, because this is only 2 groups around the central atom. But for all the others, once you have the lone pair in there, once lone pairs are present, the geometry and shape are going to be different. Okay, so over here for static number 3, the geometry is trigonal planar. If there is simply 1 lone pair, 2 lone pairs, it doesn't matter. The geometry stays the same, but the shape is going to differ. And the reason why the shape is going to differ because of the space that the lone pairs take, and the lone pairs tend to squish the bonds more. So now the groups around the central atom will arrange in a different way, causing a different bond angle. And this is why the shape differs in this case. So we're going to refer to this table whenever we are working with the geometry and with the shape. So let's have an example in here. Let's say if I gave you those and I asked you, what is the geometry and the shape for each one of those? I mean for the central atom, of course. So you're always going to look like you did for the hybridization. You're going to look at the central atom and you're going to determine how the groups are arranged around that central atom. Whenever you see a lone pair, then you know that the geometry and the shape are going to be different. So to go ahead and find out the geometry, you found out always the geometry first. So to find out the geometry, you would need to calculate what we call a static number. So simply this is the static number over here that we care about. So these are the static numbers. This is the static number column in there. So how to calculate the static number? The static number has a formula. So I'm just going to call this Sn. Sn is the static number. It's actually the number of the groups connected to the central plus the lone pair. Okay, plus the lone pair. So I would start with this A over here. Okay, so I would look and see, okay, how many groups are there around the central atom? I have one group, I have two groups, plus the lone pair, this is another group. So here the static number is going to be equal to 3. So I go to this table and I say, okay, static number is equal to 3. And how much lone pairs I have on A? I have just one lone pair. So static number of 3, lone pair of 1. Then the geometry is a trigonal planar. So the geometry for this one is going to be trigonal planar. However, the shape is going to be bent. So the shape is going to differ. The shape for this one is going to be bent. Okay? For example, 2 over here. So you calculate the static number. It's the number of groups connected to the central. That's going to be equal to 3, right? You have 3 groups in there. No lone pair on A, so the lone pair is 0. So we're looking at 3, and we're looking at lone pair 0. So the geometry and the shape are going to be the same. So both geometry and shape are going to be trigonal planar. And this is always the case whenever there is a lone pair. So whenever there is a lone pair, the geometry and the shape are going to be different. If there is no lone pair on the central atom, the geometry and the shape are going to be the same. This is another example over here. You do have 1, 2, and 3. No lone pairs on the central atom, so you're looking at the static number of 3. A lone pair of 0 over here, so see a lone pair of 0. Then the geometry and the shape are going to be the same, and it's going to be both are going to be trigonal planar. Okay, for this one, I mean, if you have 2 groups around the central atom, that's it. It's always the geometry and shape are going to be linear, no matter how many lone pairs do you have, if it's 0 or 1. So A over here has 2 groups around the central atom. This is going to be the 2 groups, 0 lone pair. So it's going to be the geometry and the shape are going to be the same, and that is going to be linear for both. So you have to differentiate between the geometry and the shape, and you have to read the question if we're asking about the shape, the molecular, or if you're asked about the molecular geometry. Let's have another example in here. So we can give you like a molecular model and we can ask you, okay, what is the shape and the geometry for this one? So you look at the central atom and count how many groups around the central atom to calculate the static number. There is no lone pair in there. So I have 3 groups around it. So again, you go 3, 0. So this one is trigonal planar, and it's drawn as a trigonal planar. All of these groups are in the same plane. So it's going to be both trigonal planar. Both the shape and the geometry, they are going to be trigonal planar. Okay, for this structure over here, you're going to calculate the steric number. You have two groups around the central atom and two lone pairs. So groups plus the lone pairs. This is going to be 4. So you go over here and say, okay, my steric number is equal to 4. And my lone pair is equal to 2. So that is going to leave me to have a tetrahedral as a geometry for this molecule here. And my shape is going to be bent. So see how the geometry and the shape, they are now different. They are apart from each other. So now my geometry is going to be tetrahedral, and my shape is going to be bent. Let's have another example. So this one has 1, 2, 3, 4, 5 groups around it. So the steric number for this central atom is 5. So the steric number is 5. And the lone pair is equal to 0. So I go over here and say, okay, steric number 5, lone pair 0. Then the geometry is trigonal bipyramidal. And the shape is the same. Trigonal bipyramidal. Why? Because I have no lone pair on the central atom. On the other hand, over here, see, this one is 4 groups around the central atom plus the lone pair. So this is going to be 5. But the difference is that I have a steric number of 5 and I have a lone pair of 1. So now see how the geometry and the shape, they aparted from each other. They are not the same now. The geometry is trigonal bipyramidal and the shape is a seesaw. So it's drawn like a seesaw. So you guys, please read the question and see if you're asked about the shape or the geometry. So this one, the geometry is going to be trigonal bipyramidal. And then the shape is going to be a seesaw. Okay. For this one over here, my steric number is going to be equal to 4 plus 2. So it's going to be 6. So when I am looking at the Vasper table, I am looking at steric number 6 and I'm looking at lone pair 2. So the geometry is going to be octahedral. And the shape now is going to be square planar. See, this is why it's drawn as a square planar. The last example, we're going to calculate the steric number around the central atom. So the steric number here is going to be equal to 5 groups around the central atom plus 1. So steric number over here is equal to 6. So I'm going to go and go to the steric number column. So it's going to be 6. The lone pair is going to be 1. So my geometry is going to be octahedral. And since I have a lone pair, the geometry and the shape are going to be different. The shape here is going to be square pyramidal.